Now, it's not the case that every time a graph touches the x-axis, it just simply crosses, right? There are other possibilities as well. For example, here we can see in the first graph, at x equals 3, this graph touches the x-axis but turns back around again. In the second graph, we can see that at x equals -1, the behavior is a little bit more strange, right? It doesn't simply cross, it does this fancy little sweep over to the side as it crosses. This is due to something that we call multiplicity. So the way to think about multiplicity is to just look in a small neighborhood about that point. So for now, let's just not look at any of the other graphs. So just sort of ignore everything else and just look at this rectangle that I've drawn right around x equals 3. We can see that locally that looks kind of like the graph of y equals x squared. It looks sort of like a parabola. In this case, it looks like y equals -x squared because that little parabolet would open down. But the idea is that it looks like a parabola there right where it touches the x-axis. Because of this, we would say that it has multiplicity 2. And that tells us that it comes from a squared factor. So instead of just coming from the factor x minus 3, which we would get from the factor theorem, this actually comes from x minus 3 squared because of the multiplicity 2. For the other 0 in this, that is not the case. The graph simply crosses the x-axis at 5, and so that would just have multiplicity 1. We usually don't talk about multiplicity when it's 1, but if we had to answer a question about it, we would indicate that its multiplicity is equal to 1, and therefore it comes from a linear factor, or a factor that's taken to the power 1. We don't generally write the 1 in this case. Now looking at the next graph, let's again draw a small rectangle around that 0, and just look at this part of the graph, ignoring the rest of it for now. This, locally, looks kind of like the graph of y equals x cubed. Remember that y equals x cubed has that kind of funny shape, right? If we were to draw in just a tiny little pair of axes and a graph over here to recall, it comes up and it flattens out for just a second and then keeps going. So when we see that same kind of behavior of a funny little twitch as it's crossing the x-axis, we would say that looks like the graph of y equals x cubed, and therefore that 0 has multiplicity 3. And you might be already guessing by now what that would mean for the factor. The factor x plus 1, which would come from a 0 of -1, would be cubed. So that 0 must correspond to a cubed factor. And the other factor in this case would be x minus 2. We don't see any fancy multiplicity going on there, so it has multiplicity 1, and we would go ahead and write that factor without a power. Just like over here on this first one, we would really write that without the power 1. So when we're looking at a graph of a polynomial and finding the zeros and building factors from those zeros, we now want to also consider multiplicity. So my first 0 looks like it's at -2. My second 0 looks like it's at +1. And it looks like I have another one at 3. I'm going to write out those basic factors. X plus 2 would go with -2. X minus 1 would go with +1. And x minus 3 would go with +3. And now I'm going to examine each of these to see if any of them has a multiplicity other than 1. Looking at the first one, I look at just a small window around that 0, and it just looks pretty simple, like it crosses the x-axis, not in a particularly fancy way. So I'm going to say that has multiplicity 1. Looking at the second 0, I can see that looks more like that y equals x squared that we identified. And because it looks like y equals x squared in that small window, I know that that must have multiplicity 2, and therefore the factor that corresponds to that 0 must be a squared factor. Finally, I go ahead and look at the third 0, and that one looks like it, again, just crosses in a simple kind of way. So I'll leave that with a coefficient of 1. Now let's do a degree check here. It looks like this polynomial is degree 4. We can tell for certain that it has even degree, and we can identify it as degree 4 either by counting the turning points or by starting to recognize degree 4 polynomials as those m and w shapes, right? A parabola is degree 2. We know what that looks like. If it has an extra bump in it, but only one extra bump in it, then it's degree 4. So this is a degree 4 polynomial, and if I add up all the powers of these factors here, I get a power 1 plus 2 more plus 1 more, which is 4. So it looks right. If I miss a multiplicity somewhere, my degree check really shouldn't work, right? I should be able to catch it at this point. And the reason we're adding up these powers is that if I were to multiply out these factors, I could see that I would get x to the 1 from the first one. I would have an x squared after squaring the binomial in the second one, and I would have another x to the 1 in the third. And when I multiply all those terms together, I would end up adding the powers to get, x to the 4th. So if we just add up all the powers, we can tell what degree that polynomial should have. I still need to think about the leading coefficient. I always look back at the instruction to make sure that, that it tells me the leading coefficient is -1 or 1 before assuming that. Assuming the leading coefficient is -1 or 1, so that all I have to figure out is whether it's negative or positive. In this case, the leading coefficient appears to be positive, which I can tell from the end behavior. An even degree polynomial with a positive leading coefficient has the ends going up. So that my final answer for this whole function would be just these factors with no number other than 1 multiplied. Therefore, I don't have to write a coefficient onto the start of it. It would be a good idea to pause this video and try the next one on your own, and then check and see if your answer agrees with mine. I will start by finding the zeros. We have a 0 at -3. We have another 0 at 0. And we're going to have factors x plus 3 and x minus 0. Of course, I'm going to get rid of that -0 by the time I'm done with this, but just to make it really easy to see which 0 each of these factors goes with, I will leave it there for now. Looking at a small window around this first 0, it looks like it has multiplicity 1. So I'll go on to the next one. Looking at a small window around this second 0, this looks kind of like the graph of y equals x cubed locally, and therefore I'm going to assume this has multiplicity 3. Finally, I want to figure out the end behavior. I can tell this has even degree because the ends go in the same direction, and the fact that that direction is down tells me that this has a negative leading coefficient. So I'm going to go ahead and put a negative in front of these now. For my final answer, I'm going to change this factor to x cubed, And it's more common to put the monomial factor first. If you have any factors that have only one term in them, it makes sense to put those first because that's the way the polynomial usually just looks most natural. So I would write this as minus x cubed times x plus 3. Again, doing that degree check, we can see that this is a degree 4. Counting the turns on something like this, we would have to treat this as 2 turning points. Even though it doesn't turn all the way around, that does add 2 to the degree having this kind of pattern. So we'd have a turn up here and 2 turns down here for 3 turning points in a degree of 4. Or we could figure out that this has degree 4, again based on that idea that it's certainly not degree 2. The degree 2 would be a parabola, and it doesn't look like it has enough more added kind of bumps and turns to it to go all the way up to degree 6. So it makes sense, knowing that it's even degree, to say that it has degree 4. So for our degree check, we've got 3 plus 1 equals 4 down here. It looks like we probably have everything covered.